All right, welcome back. So we are going to continue with partial fraction decomposition, the act of integrating a polynomial over a polynomial where the degree upstairs is less than the degree downstairs. So in principle, you could imagine yourself given something like the integral of x plus 4 over x minus 2 times x plus 1. Yes, downstairs, that's not evidently a polynomial on the surface just based on the form. However, if you imagine foiling that out and collecting like terms, you would get a degree 2 polynomial downstairs. The numerator degree is less than the denominator degree, so we satisfy the criteria above. And as we know from our previous video, the general form, whenever you take a fraction of polynomials where the degree downstairs is greater and you have just degree 1 factors downstairs, we're going to take each of those degree 1 factors, write them in their own individual fraction with a lesser degree 0 constant upstairs. So a and b are just constants, and really our goal here is going to be to find the a and the b which satisfy this equation. So I'm going to pause the video here real quick and then we'll walk through the computation. All right, so in order to find our capital A and capital B, we really want to get the right-hand side here communicating with the left-hand side, and the left-hand side is written over a common denominator. So maybe we take this sum and write it over a common denominator. Well, to do so, the first fraction would have to get a factor of x plus 1. In order that we don't disrupt the value of this fraction, we multiply by that same x plus 1 on top and bottom. This second fraction, to get the common denominator, would need a factor of x minus 2, and in order to not disrupt the value of this fraction, we multiply x minus 2 to top and bottom. So if we now have a common denominator, x plus 1, x minus 2, on each of our fractions, we could put those numerators over that common denominator. The first numerator would be a times x plus 1, and the second numerator would be b times x minus 2. Now, observe, between these two expressions that we've conjured up, they both have the same denominator, and they are equal fractions. Well, if equal fractions have the same denominator, they also have to have the same numerator. And so the numerator on this fraction and the numerator on our original fraction must be equal, which is exactly what is said below. Ultimately, by doing this first sort of setup, we've got that x plus 4 is equal to a times x plus 1 plus b times x minus 2. And at this moment, there are going to be two ways in which we can proceed with the result. So one of them is going to be option 1, using old school algebra. The other is going to be option 2, evaluating to reduce variables. We'll break down each of these processes. I'll start with option 1. All right, so as far as option 1 goes, using old school algebra, we're going to take the expression that we had, x plus 4 equals a times x plus 1, b times x plus x minus 2, and we're essentially going to distribute out the right-hand side. So this will give us, I'm going to collect the two x terms together. So we'll have an ax and a bx, and then as far as the number terms go, we'll have an a minus a 2b. Note the minus 2 on that, note the negative sign on that 2. And so, well, now that we've gotten to this point, what I'm next going to do is I'm going to sort of collect all the terms associated with x, namely the a plus b. So essentially factor out the x from the two terms that have the x, and then the two terms that don't have the x, leave them by themselves. I'm going to be emphatic here. Where we had x plus 4, I'm going to write as 1x plus 4, just to remind ourselves that, nothing written in front of x means that we have exactly one of those x's. But now, comparing the left-hand side to the right-hand side, you can see that 1x plus 4 is equal to this times x plus that. Well, that means 1 and a plus b have to be the same in order for the two sides to be equal, right? Because the a plus b is what's being multiplied by x, and the 1 is what's being multiplied by x. In other words, we know that a plus b has to be 1. Similarly, the 4 is the number that's hanging out to the right of the term involving x, and the a minus 2b is the number that's hanging out to the right of the term involving x, which means a minus 2b has to be 4, which gets us to this point. And now this should flash you back to old school algebra, because we are a substitution or an elimination process away. If I was going about this, I'd probably multiply the top one by 2 to get 2 equals 2a plus 2b, setting up for an elimination with my b's, because now my b's would be equal in magnitude, opposite in sign, and when you add the two equations to one another, the b's drop out, you get 6 equals 3a, and ultimately what? A equals 2. Now, once you have a equals 2, it's just a matter of going back into either of the original two equations to figure out what b is. I like the top equation because 1 is the sum of a and b. Well, if a is 2 and a and b sum to be 1, you know what b has to be. B has to be minus 1. And so, hey, look, we've resolved the issue of trying to find the a and the b that decompose this particular function. We did it with old school algebra, sort of flashing back to a two-variable, two-equation system. So perfectly fine way to deal with things, yet there is another option, and I want to show that as well. But I do want to emphasize the fact that old school algebra is like beautifully stout at dealing with these partial fraction decompositions. But let's check out option 2 as well. All right, as far as the evaluation goes, option 2, let's check it out. So recall, as we had worked through our getting common denominators and then viewing that we had equal fractions with equal denominators, hence equal numerators, we had this x plus 4 equals a times x plus 1 plus b times x minus 2 expression. Also note, on the right-hand side, the x's, which would zero out the factors that appear here, would be minus 1, would zero out this x plus 1 factor, and 2 would zero out that x minus 2 factor. But yet these two sides are equal. So hey, if these two sides are equal, they should evaluate the same no matter what the x is. So what we're going to do strategically is insert an x equals minus 1. If you insert x equals minus 1 to the left-hand side, you'll get 3. Insert x equals minus 1 to the right-hand side, and you'll get a times 0 plus b times minus 3. Now, a times 0 goes away. That's actually why we chose x equals minus 1 strategically. And then as a result, then, we would have 3 equals minus 3b. But that tells you what b has to be. b has to be minus 1 in order for that to be true. Because if b was minus 1, you'd have minus 1 times minus 3 equal to 3, and life would be beautiful. Well, we found b by simply plugging in an x that got rid of the a within that expression. What about plugging in an x that would get rid of b in the expression? That would be plugging in x equals 2. So if we evaluated x equals 2, x plus 4 becomes 6. We get a times 3 equals b times 0. But hey, b times 0, that cancels out. And then all you have is 6 equals 3a. But 6 equals 3a means that a would have to be 2. And check it out. You get the exact same answer as you got via old school algebra. Actually, looking at the amount of symbols that were required to push, I kind of prefer the evaluation mechanism, although I will say this cautionarily. The decompositions that you experience could be complicated enough that evaluation is not always the best way to go, and having to rely upon old school algebra can be ultimately a necessity in certain cases. So I'm going to pause the video here, see where time's at, and then determine how to proceed from here. But at the very least, we've gotten through a complete exercise of finding the a and the b for our particular function. To be very clear about this, just to summarize what the end result we would have, because the a and the b were within our original x plus 4 over x minus 2, x plus 1 expression. Essentially, the end result of what we have here, let me write it in this space here, is that x plus 4 over x minus 2, x plus 1 is equal to, well, what was our a? Our a was 2, and so we have 2 over x minus 2, and what was our b? Our b was minus 1. We'd have minus 1 over x plus 1. And so I'll put this box here to sort of show the end result of our work, but what we have deduced is that this original ratio of polynomials that would have been pretty tricky to integrate can now be decomposed into a sum of polynomials that are really not that hard to integrate. And that's the goal, frankly, of partial fraction decomposition, and at least we've seen it in this one manifestation.